Hello, my name is David Ackerman, student number 220-310-629, and this is the MEC 2302 Mandatory Assignment 6. This is Part A, Part B, and Part C with all the givens. These are the two diagrams for Part B and C. And now let's get to the analysis. So for Part A, this is the diagram schematic where it has the force F is force of friction, G is the center of gravity, mg is the force of the box, ma is the force of acceleration. Then here also and here's the crate's mass is small m, which is 150 kg. The cart's mass is big M, which is 10 kg. The coefficient of friction is mu s, which is zero point 0.2. G is the center of mass, and we're looking for P, which is the force in newtons. So the assumption here is that the uniform weight distribution for the boxes. So at first, we want to use the equilibrium equation of motion of the crate at the y-axis. So the forces, or the sum of the forces in the y equals MAY, and we find out that MA is actually zero, so we cross that out and we put mg to the other side. So the normal force equals mg. So now we plug in the mass of the crate and the force of gravity and the acceleration due to gravity, and we get this number. Now we've got the equivalent equation of motion of the box at the x-axis. Again, at the x-axis there's only friction, and there's the ma, which we're solving for acceleration. Friction equals to mu normal force. That's why we need the normal force. And then we divide both sides by the mass of the crate to isolate for A. We plug in all the variables and we get that the acceleration is 1.962 meters per second squared. Now we do on one more equilibrium equation of the moment at A, which is sum of the moments at A equals the sum of the moments at KA. There's mass of the crate on both sides, so we nullify that, we cross that out. So we get the force of gravity X equals the A the times 0.5, which is the moment. And then we isolate for X by dividing both sides by G. We plug in all the values and we get X equals 0.1 meters. As x equals 0.1 meters, um, which is less than 0.25, the crate would indeed slip before it tips. So this is the free body diagram of the completed system. If not drawn before, I just did a different one here. There was a force P back, the normal 1, normal 2, mg, and the acceleration. So we do one more equilibrium equation of motion at the horizontal direction of the box, meaning that we take the both masses, we factor the A out, and we find out that the P is the sum of the forces in the X is P, and we plug in all the known variables, which is the mass of the crate, the mass of the cart, the acceleration that we found a step earlier, and we get that 3.13.92, which is the max allowable force, given the conditions. So part B, the given would be the force that we calculated, the height of the bigger man, which is 1.7, the angle, which is 30 degrees, and now we're trying to find the allowable force for the guy. And the assumption is that no components would be used to be lifting the actual crate. So all the forces are going to be used in the horizontal direction. So this is the diagram where P hypotenuse equals the P allowable or P allow. P in the X is 313.92. So we use the trigonometric ratios SOHCAHTOA, TOA. We use Ka, which is cos over adjacent over hypotenuse, equals 30 px over p allowable, which is we're looking for p allow, so we isolate that, plug in all the no variables, and we get the p allow equals 362.48, which is the max allowable force for the bigger man. So question question C is asked for um, elaboration, and to accommodate both individuals equally, an adjustable handle height can be implemented, allowing the force application from an optimal position, regardless of the height differences. So someone just as really short can pull just as much weight as someone who's really tall. Alternatively, a pulley system or lever mechanism could also be standardized as a direction, ensuring that a consistent application of force, so it would maybe make the force a little bit easier. A simpler solution is providing maybe a step up or a platform for the shorter person to match the taller person, the force angle. This would be dependent on the height of the person, but it would be an easier solution. These solutions are effective effectively preventing tipping or slipping while being quick, cost-effective, and easy to implement. This has been my assignment 6 solution. Thank you so much for listening.